Namaste and welcome to the lecture series on mathematical foundations for machine learning. In the last couple of lectures we have looked at the idea of calculus and this is motivating towards the optimization that we will be doing. Machine learning especially is all about optimization and stuff. So we started looking at the idea of calculus because somewhere we have studied in our class 12 or something that if you want to find out the maxima or minima, you have to look at some kind of you have to look at derivatives. You have to take the help of derivatives to look at maxima or minima and so on. And in the process we also looked at what a derivative was, and then we tried figuring out the higher order derivatives, and then we chose a very specific case where we use these derivatives to construct a function or to construct a power series expansion for functions. And we looked at the Taylor and Maclaurin series and stuff, where Maclaurin series was basically function evaluated at a particular point and derivatives, all the higher order derivatives or all derivatives evaluated at the same point, and which is x is Maclaurin series was at x is equal to 0, and we said that Taylor series, generalized Taylor series, was evaluating the function at some point, let us say x equal to x naught, right. We saw that, and subsequently we took the we looked at the rules for taking the derivatives and so on. So we saw that the derivative of a sum of function is nothing but the sum of derivatives. Therefore we also brought in our idea of linear transformation, which we studied in the second week of this course, where we said that transformation on the linear combination of the vectors is nothing but the sum of the sum of transformations that you had, like on the individual vectors. We said that transformation on alpha x plus alpha u plus beta v is nothing but alpha times transformation on u plus beta times transformation on v. So we said that the same way the derivative of a sum is sum of derivatives. So derivative or differential is nothing but a linear operator. Then we also studied subsequent rules where we looked at the derivative of product of functions, and we were hoping that the derivative of the product of functions to be equal to the product of derivatives. Unfortunately it did not turn out that simple. We figured out it is much more than what we thought, what we actually thought. We also looked at the derivative of f of x by g of x, and when we concluded the last class we looked at something very interesting where we looked at the chain rule. Basically we looked at compositions. Basically we said f of g of x, then if you want to look at the derivative of f of g of x, then we figured out what it was. We saw that it was basically something like this. So we actually looked at so we said that the derivative is nothing but the derivative of the function f with respect to g and then the derivative of g with respect to x. So that was the derivative of a composition. And now what we are going to do is we are going to look at the idea of partial derivatives in this class, and we will also look at the chain rule as employed with the partial derivatives. Okay, so let us get ahead. Before getting into partial derivatives we need to clear a lot of ground. So what we will do is we will look at the basics of where do we get into this idea of partial derivatives. Here we never used the term partial derivative when we said y is equal to f of x. We just said take the derivative of y with respect to x, that is it. Now what does this partial derivative mean? Why are we even studying that? What does it convey, right? How do we take the partial derivatives, right? So those things will form the core of today's lecture. So what we will do is we just do a quick recall. Y is equal to f of x. This was basically a map from R to R, map from R to R. Now what does it mean? The function took a real number and gave me back a real number, right. and what is very interesting is this y is equal to f of x is basically a curve in the xy plane, right. It is basically a curve in a xy plane. I mean, it could also, it is also including line or whatever it is, it is a geometry in the xy plane. So what we are going to do is, this is basically a geometry in the xy plane. Where the x variable, you know that it is the independent variable and y is dependent on x. So you plotted that as the dependent variable. So you basically plotted the function, you can plot the function, the moment you are given f of x you can always get the graph of that function, right. So geometry in xy plane, so typically we will take this as a curve in xy plane. Now what are we going to do is, we are just going to add one more dimension to it. What is that? We want to say, look, I am not going to talk about y is equal to f of x anymore, I am going to talk about z is equal to f of x comma y. Z is equal to f of x comma y, that means I have this, I have brought in my third dimension also. I have this x direction, I have this y direction, and the function I am going to plot it in z direction, right. Oh, basically, so what does this function do in that case? This function z that you have, which is equal to f of x comma y, what does it do? It is going to take two real numbers x and y and then give me back one real number z. So this is going to be a map from R2 to R. This is a map from R2 to R, right. And where does the function reside? The function actually is there in 3-dimensional space, right. The function basically, it's basically whatever you have here is basically a surface in 3D space. Right. So what does that mean? What problems are we going to face if you are going to say, look, I am going to add one more variable, an independent variable, and this function is going to be a function of two independent variables. So what problems are we going to face as far as derivatives are concerned? Because I will restrict it to the context of derivatives, because I mean any other thing is not in the purview of the current context that we have set, right. Okay. So how are we going to do this? Let us take a simple example. Let us consider this function z is equal to let us say f of x comma y, z is equal to f of x comma y is equal to square root of x squared plus y squared, square root of x squared plus y squared. And again, if you have done 3D geometry in your in class 11 12, you will see that you are seeing that this is going to be a, what is this going to be? This is going to be a right circular cone, a right circular cone. Now I understand that it is a bit tricky for people who have done high school mathematics long time back to bring back these ideas, but bear with me because I need to do it so that we drive home certain points, right. So it is a right circular cone with vertex at 0 comma 0 comma 0, vertex at x comma y comma z is equal to 0 comma 0 comma 0, right. So basically we have okay, anyway, so this is a right circular cone with vertex at x comma y comma z is equal to 0 comma 0 comma 0. Now what we want to do is, we want to look at this. Suppose I fix I want to do something, I want to fix let us say z is equal to 4, z is equal to 4, which implies f of x comma y is equal to 4, which is equal to square root of x squared plus y squared. Now what does this actually mean? It is like saying, look, I am going to have z is equal to 4, I am going to have a plane to intersect this cone at z is equal to 4, that is a plane that we have. So what do we have at z is equal to 4? This is nothing but it is going to contain a circle of points at z is equal to 4. We are going to have a circle of points at the same height or level or the height or the level of the surface. So what does it mean? This is basically saying, look, I have a constant c, I am going to say f of x comma y is equal to c. Right, f of x comma y is equal to c. What am I going to have? I am going to have a set of points, set of all points, let us say x comma y at f of x comma y is equal to c, which means all these points will have the same value f of x comma y is equal to c, right. And what do we do with such things? So these things, this set of points that we have, this is basically what we call as level curve. This is what we call as level curve. What do we mean by this? I mean, you can even look at let us say, for example, just if you look above your head in your room where this fan is rotating, the fan is at a certain height, the room is a 3-dimensional space and the fan is at a certain height, and at that height is constant, the fan is not going to fall down or go up, it is fixed at that particular height, and you are going to have a set of points, that is basically a plane that you are going to have. So you are going to have a set of points at that particular level, and that set of points will constitute a curve, and that is what we are going to call as level curve at a particular level. At a particular height the function is constant and the set of all points that you get is what we call as the level curves, right. Now let us look at this simple example. When we look at f of x comma y is equal to square root of x square plus y square. So I have f of x comma y is equal to square root, z is equal to this, you have x squared plus y squared, right. Now suppose if I put z is equal to 0, I am going to have x comma y to be equal to 0 because it is sum of squares. Sum of squares can never be equal to 0 unless the elements that you add are going to be 0. This is going to give me x comma y to be equal to 0. So this is going to be a point, that is going to be a degenerate circle. So you are going to have a point, so x comma y is equal to 0 comma 0. So just a point. Now what I am going to do is I am going to say, look, z is equal to 1, then I may have a set of points for which is equal to square root of x square plus y square. So I would end up getting a circle there. Z is equal to 2, another circle, and so on. Now what we see is for different values of z you end up getting different circles of different radius, right. When I say for different values of z, it simply means that I am going to look at different heights or different levels, and at each height because the structure that I've gone, the geometry that I've looked at is basically a right circular cone, at every z is equal to a fixed value I am going to get a circle, but the circle is going to have different radius, right. This is what we have, and we are going to give a name to this. So what are we going to do? We are going to say that the collection of level curves of a function, we are going to give a name. This is called as the contour, right. This is basically the intersection of functions graph, right, intersection of functions graph with a horizontal plane at that level. Right. So this is what we have. Now this contour is also not something which you have not studied. Contour is something which you have studied where? Contour plots we would have studied in geography, high school geography, where you would have been given mountainous range, and then at different altitudes it is going to look at that. So at a different altitude corresponds to a level curve, and you get the contour map there. All these things we have done. It is not that we have not done, we have done, just that we would have forgotten it long time back, or probably we would have felt that okay, I am not going to use this anywhere, but look at where we have come. All that we have studied before are now coming to haunt us again, right. So this contour is something which you have studied already, which is a collection of level curves of a function. Now let us take an example. Let us take another example here to study what is the contour plots, whatever that is. So suppose I have this function, I have this z is equal to f of x comma y is equal to x plus 2y, right, x plus 2y. X plus 2y is basically a plane in 3D. You can write z is equal to x plus 2y, and which is nothing but x plus 2y minus z is equal to 0. This is something which you have seen even in our linear algebra. This is a plane in 3D, right. Now so what are the level curves corresponding to this plane? Oh, that is something interesting. When we took cone, we said that look, the level curves are all going to be circles, so you are going to have the contour to be concentric circles with the center point or the vertex to be at 0 0 0 0 and 0. Now I have this function which is basically a plane in 3D. So what is going to be the level curves for here? So what are the level curves? So now I will put this, suppose I put z is equal to 1. So what do I get? If I say f of x comma y is equal to 1, what do I get? Z is equal to 1 implies this is equal to x plus 2y. So x plus 2y is equal to 1, what is that going to be? That is just a straight line. Now if I put z is equal to 0, I get another straight line which passes through the origin. Then I put z is equal to minus 1, I will end up getting another straight line which is with the same thing. So you are going to have parallel lines here, right. So the level curve for this function, the level curve for f of x comma y is equal to x plus 2y is basically set of lines, is a set of lines in xy plane. in xy plane, right. Yeah. Interesting. Now why are we even studying all these things? What is the use of this level curve? Why do we study contour? Right? We'll come to that in a few minutes, but before we get on to that, let's just look at this. So what we have in these cases where I said f is a function which is going to map from R2 to R. That means f is going to take two component vector, let us say x y, and it is going to map to a real number, let us say z. That is what it is. Okay. The moment I say it is a two component vector, that means there are two directions, we know that x direction and y directions are there. That means the function z is going to depend, z is equal to f of x comma y depends on both x and y, depends on both x and y. So what? So what is the big deal about the function being dependent on both x and y? Oh, the deal is we looking at the derivatives. We are not going to look at just like what we did in case of the one dimensional or in case of the functions of single variable, where we said the derivative is nothing but rate of change of instantaneous rate of change of the function, right. We said dy by dx is equal to f of x naught plus h minus f x naught divided by h with limit h tending to 0, we said that. Oh, here this function is going to depend on both x and y, which means there could be instantaneous rate of change along the direction of x, there could be rate of change along instantaneous rate of change along the direction of y. That means this function is sensitive to both the variations in both x and y direction. Therefore what should I do? I have to use a different idea of derivatives, because it has to capture variation along x direction and variation along y direction. So how are we going to do that? And that is exactly where we get into the idea of partial derivatives, right. So what we do we get to the idea of partial derivatives, we say that we keep one of the variables constant, and vary the other. Right, we vary the other by and we fix one of them. So what we do here is we are going to define the derivatives. No, we are not going to call them as the derivatives, instead we are going to call them as the partial derivatives. So partial derivative of the function f of x comma y, which is say z is equal to f of x comma y, are basically denoted by given by I will use this notation f sub x, right, f subscript x, to indicate this, that this is the derivative with respect to x. F sub x is nothing but dou f divided by dou x. I am going to use this notation dou, which is basically the partial derivative identifier. So I am going to say dou by dou x of f, and I am going to say f y is nothing but dou f by dou y, right. And together you are going to call this as your derivative of the function, right. So this is basically the derivative of the function with respect to x, and that is with respect to y. So these are called as the partial derivatives. So how are we going to do this? We need to look at it from the first principle. So how are we going to do this? I am going to say dou f by dou x is nothing but limit h tending to 0 f of x comma y, right. Where is the problem now? I am going to keep y constant. So, I am going to say I am going to vary along h f of x comma h comma y minus f of x comma y divided by h, and that is what I am going to call that as the partial derivative of x with f with respect to x. Similarly, I can do dou f by dou y, which is nothing but limit h tending to 0 f of x comma y plus h minus f of x comma y. That means you have already fixed the value of x, just giving a small nudge in the direction of y. So, which is going to be f y, right. This is what we have. Maybe let us take a let us quickly take an example and see like what is this you know the partial derivative of these functions. So, let us just take an example. Example 1. So, I have let us take this. I have f is equal to f of x comma y is equal to x squared plus y squared. This is not something that you would not have seen before. You would have seen it in the context of vectors, as suppose I take a 2 component vector, the length of the 2 component vector is basically squared length is nothing but x square x1 square plus x2 square, right, recall. The norm of a vector x is norm squared is basically given by where x vector is equal to x1 x2, the squared norm is given by x1 squared plus x2 squared. So, what is it that we understand? We see that for a 2 component vector, the norm is basically a function which is like what you are seeing now, which is a function of 2 variables x1 and x2, and then it is going to give me a real number. So, I have this x squared plus y squared. So, what I will do is I will take dou f by dou x is nothing but 2x, and dou f by dou y is equal to 2y, right. Let us take one more example, example 2. I am going to say f of x1 comma x2 is nothing but let us say x1 x2 squared plus x1 cube x2 x1. So, what is this going to do? This is going to map this is a function from R2 to R. So, what is dou f by dou x1? Dou f by dou x1 is nothing but x2 squared plus 3 x1 squared x2, and dou f by dou x2 is nothing but 2 x1 x2 plus x1 cube. This is what we have, right. So, these are basically the partial derivatives. We will take another slightly complicated problem and try to work that out. Example 3, I have f of x comma y, or we will take the same example which we did in the beginning, the right circular cone x squared plus y squared. So, dou f by dou x is nothing but dou of square root of x squared plus y squared by dou x, which is nothing but 2x, basically it is a composition again what we see. So, this is basically square root of, if I take x squared plus y squared is equal to u, I will come to the chain rule a bit later. So, you could apply chain rule here also. So, this is I am going to take x squared plus y squared to be equal to u. So, I have dou u by dou x is nothing but 1 by 2 root u. So, I am going to have by 2 root of x squared plus y squared into dou u by dou x. So, that will become 2x. So, these two will get knocked off. So, what I have is x by square root of x squared plus y squared. Similarly, I will take dou f by dou y. Dou f by dou y is nothing but y by square root of x squared plus y squared, right. This is what we have. So, So what we have done is we have now collected the partial derivatives and so on. So what are we going to do with this partial derivatives? Does chain rule apply to partial derivatives also? How are we going to, I mean, so one more thing that we want to look at is like, look, we took higher order derivatives also there in the case of single variable. Now are we allowed to do all these things here? So those are the questions that we have. So what we will do is like in the next class when we come back, we will look at the ideas of we will reiterate the ideas of partial derivatives. We will capture them in terms of what we call as the gradient matrix. So we will call this as the gradient. Then we will look at the idea of what you call directional derivatives, right. We will look at directional derivatives, and then we will go ahead with higher order derivatives and more, right. Okay. So in this lecture what we have done is we looked at what happens, what is the difference between the geometry that you get in a 2-dimensional plane and then what is the geometry that you get in a 3-dimensional plane. In 2-dimensional plane it is just going to be a curve, in a plane xy plane it is just going to be the curve, and if you are going to look at 3D space it is going to be a surface that you are going to get, you surface, and when the function is going to take a constant value you call such set of curves to be the level curves, collection of level curves you called it as contour. And then we looked at we figured out that look, when you have a function of multiple variables, in this case 2, the rate of change is along both the directions, therefore we wanted to individually study these two guys. So what we did is we took the partial derivatives, we brought in a new idea, we fixed the value of one variable and then varied the other. Basically we kind of gave an incremental change in case of one variable keeping the other constant. So we got the partial derivative with respect to x and with respect to y, and we also did some examples. So when we come back to the next class we will answer a couple of questions like how are we going to organize all these partial derivatives. We look at the idea of gradients and then we look at the idea of directional derivatives, and subsequently we will look at Jacobian and Hessian and so on. Namaste.